Let's talk about the sorted array collection. So this Java class is available in your modules. This particular Java class is very similar to the array collection class from the previous lecture, with a few differences. So the very first difference is we're using unbounded methods to grow the size of the array. This happens when the underlying buffer runs out of space. So we call this enlarge. So if you recall from the array unbounded queue implementation, this is exactly the same thing. The other difference is now we're using the find method with binary search algorithms. So this allows you to search target very, very quickly. As you recall, binary search calls for O log n, right? Log base 2. Now, the other difference is, obviously, when we're talking about array collections, the elements inside of this underlying buffer must be sorted, right? So this means that every time we add and remove elements, we must preserve the underlying order of the array. So that's where the expense is, because you have to make sure, when you add or insert an element, it must be slotted in the right position. And removing it calls for the same thing. Last difference being these elements must have a comparable method to allow for the ascertaining of their order relative, or the quote unquote relative size, right, to each other, to allow you to to see where you are, right? If there is no sense of the order or size of these elements comparing with each other, because remember the elements inside the array does not have to be integer, okay? So it could be string, could be some object. So you have to implement these things to allow for that sense of orderness. Without this, this implementation is impossible. Okay, so without further ado, let's kind of just move forward and see what we have here into the next slide. The pictorial representation of the add and remove. Assuming in this case, we are inserting a string object. The string object is ordered alphanumerically, in this case, in the ascending order. So A is greater than B is greater than P, and so on and so forth. If the elements that you're trying to insert is called BOL, B kind of slots in between index 0 and 1, right? So what you need to do is to make sure that you shift all of the existing elements that is occupying starting at this location forward by 1. So that opens up a space for BOL for insertions, right? So assuming BOL is that location index, so if this is location index, or this index is that location, right? So in this case, it's 1. Then what you need to do is starting at location plus 1, all the way up until the number of elements that you have, minus the BOL, minus the preceding index location. This is where you need to kind of shift this to all the way through. Same thing too, if you were to remove a element called BOL, then what you're doing is you're leaving a vacuum here that needs to be filled, right? So once this is removed, now your number of elements decreases by 1. You have to then start shifting everything right backwards, okay? Now, this is where the expensive part is. The expensive part is the copying option. So each copy is O of 1, right? But if you have O of n, you have an n elements, that's O of n right there. So add and remove is somehow expensive when you had to kind of push everything in, into the right spot. So that way you don't leave any, nullified space, and showing that there is a continuity involved in where the elements are sitting. So that is the part. But on the upside though, because every single element is kind of ordered, right? You can enable a binary search on these elements. So recall that adds and remove these transformers, including contains and get, they all have to incur, at least O of n, right? In the prior example where you didn't have this sorted to do a find, right? But because the find makes use of binary search in this example, O of log n, right? Find is extremely fast, right, compared to the old one. But now the incur expenses now for add and remove, you had to kind of shift these things over by 1 to the destinations, depends on where you are. But I would say, like, overall, thinking in terms of both find and add right inside these specific implementations here. We're looking to the specific examples here. The overall cost is still, outweighs, the add, remove, and shifting of the elements. So if you look at the application results here, this is just the text, right? And then the file size. So as you can see, the file size is actually growing in this directions here. And if you use the array collection versus sorted array collection, so one makes use of O of N sequential search, and the other one makes use of the binary search here. The difference between this method and that method in terms of the amount of time it takes to get this right, this vocabulary word experiment, it's incredible, right? As this file size goes up, you can see the array collection approach takes about 10 hours, and the other one is 7.2. And this is because of the find, okay? The underlying find. Underlying find is now O of log n versus O of n, okay? So this is huge, right? The amount of time it takes. This goes up exponentially, right? Versus where you have a log n, right, time. Sorted array collections that makes use of collection interface. So these things are very familiar to you. Hopefully the original cap for the enlarge methods, right? Every time when there's not enough space and you want to enlarge by the original size of the underlying buffer by original cap, and then basically just copying everything from the old cache into the new cache, right? So this is on the unfolding of the indices that you have from the elements, which is this is the old one, right? So let me just annotate this. This is the old buffer, right? Elements. The new buffer is the larger one. So this is the new one. Okay, it's a new buffer and the old buffer. So copying everything from old into the new one, expanding all the indices out so that you have sufficient sequential indexing, and at the end, making sure that the elements, which is the global buffer label, is now pointing to the new one. Okay. So what's going to happen to the old one that you had there is simply garbage collected. Okay. So you can dynamically instantiate it in there, and then just later on, making sure that when you copy everything over to it, you assign, the reference to elements to the larger ones. So now the element buffer now points to the larger one. Okay. So that takes care of the standard construction constructors as well as the enlarge. Let's move on to the next one. I'm going through this relatively quickly, because we already went through this in a similar implementation details when we were talking about Q. So let's look at the find. Find, as we were alluding to earlier, that we're using binary sorts. So before we do that, let's set the location to 0, found false. If this is not empty, then we're going to recursive find. So ultimately, you can change this into a iterative method, but in this case, we decided to use recursion. And recursion starting with the target, first, and last, right? Because every single time you recurse into it, remember recursion calls for 3 criteria. One is the base case. So what is the base case? The base case is basically saying this, right? When you're starting to find a target inside this buffer, the first is always 0, and the last is num element is 1, right? So at some point, this first and last, so this is last, this is first, it's going to kind of converge right in the middle. So depends really on whether your element has even number or odd number. So this underlying collection could have even number of elements, okay? And you can also have odd number elements. So if you have odd number elements, then the midpoint is going to be, pretty much right in the middle. And if you do a comparison, so the middle part is not what you were looking for. There's no way for left and for first and last to kind of even, to switch place. But let's say if you're at the even, elements buffer, your first and last is already at here, and there's no midpoint, right? This is just the nature of the underlying buffer that we're looking at. Then you have to actually make another comparison that crosses F to the other side to L, and that will result in this first greater than last. So that said, the underlying base case is already established, right? Either this or this. And the fact that every time you recurse, you're shrinking the problem. So divide and conquer allows you to break it down into a smaller size. So that second criteria also establishes. And the fact that you can establish basically write out the whole recursion using this formula here, which case this, right, or this, signify that this is a recursible problem. Anyway, so using recursion and the binary search to define your target element also assumes that your underlying target is comparable. Okay, so what does that mean? So let me just clear this out and use a different color. So because using the examples that we have there, we have string as an element. A string already implements comparable, right? This is the Java native implementations. And so if you were to want to make use of the compare to, you have to make sure that your target, as well as the elements that you're comparing to, are both comparable, meaning they could be casted to a comparable object. So if the target is a string, right, comparing to another string, then we know string is good. String implements comparable. If you don't know whether the object that you're comparing to implements comparable, you should definitely check Java ID SDK or JDK to make sure that's the case first. But in making sure that a target in both the underlying buffer implements comparable for the element, you have to, otherwise there's no way you can make use of these comparisons here. So that is the assumptions, and the rest of it, this is all binary search algorithms that we went through. The only difference being checking to see if left is greater than the right makes use of the compare to. So this compare to in the examples that we have is actually part of the string. So string dot compare to, and then you're trying to compare what's in the locations here. Anyway, I don't want to get into too much details here, but if your result equals 0, that means they're the same, right? You found the elements that you return true. Otherwise, you're going to keep on going until you find it. So this is O of log n, okay, base 2. Okay, it's extremely fast, right? When n goes up, your complexity, goes up by the log n. So as compared to O of n. Let's look at both add and remove. These two are important because these are the cornerstone of keeping track of the elements in the order that we wish. So both add and remove, again, just like your other like contains and get, calls for find. But before we do that, we have to make sure that we're not at capacity, right? So if this is already at capacity, then you need to enlarge. This is the same approach that we had for Q. But let's look at this find. First of all, you do so this find is a wrapper for the recursion. So if you scroll up here, you'll see find right here. And this find actually does the initialization of your locations and found, checking to see this is empty, and then recurse everything in there. Ultimately, you're going to get locations and found. The reason why we do this and reset this is because you could have had your location and found from the prior, right, insertion or deletion of the element, or through add and remove. So it is important every time you recurse from scratch that you need to have a initialized set of elements in there, values in there. So both add and remove calls for find first. Once found, then what you need to do is to make sure that you do the expensive one, right? So the shifting part is actually happening here as well as here. So when you remove something, you have to back shift, right? Shift everything back. But when you are adding something, you're inserting something right in the middle, potentially, right, depends on where that target is, you have to shift everything to the right. So one is to the right, one is to the left. This is O of n, and this is O of n. Okay, if you look at the complexity total, right? So this find plus O of n is O of log n. So total complexity for add is actually O of log n plus O of n, which is really not that bad, right? And the remove part is the same thing. It's O of log n plus plus O of n. Okay, and this is only good. And this will be actually, see, when n is very, very large, what you end up having is a very, relatively smaller number on the search part. And this is not always bad, right? Depends on how many elements you have there. And sometimes the target could be all the way at the end of pretty much the buffer already. So your O of n is really not O of n, it's probably O of 10 or O of 20 or something like that. This is if, your location is at 0 position, right? The very first element. But then again, your find is going to be extremely fast if this is already at the first. So there is a compensating mechanisms here that, you only get into the situation where you are really absolutely very, very unlucky. So that calls for both add and remove. And the contain is just finding, right, the targets using O of log n in this case. So this is log n, okay? All right, so this completes the walkthrough of your sorted array collection.